I guess my interest in science came from experiences with little chemical kits that change colors. I think it's always exciting to suddenly see something turn from colorless to bright purple or green.
The fact of the matter is that when I was young, the most driving ambition I had was to get off the farm. That was central. And, you know, as things worked out, chemistry seemed to be interesting, moderately easy. At that time, it was quite glamorous, or considered so. And I found out that they paid you for doing it.
Whatever the reason for first being drawn to the subject, chemists have to approach problems in a very pragmatic way. That's what we're going to examine in this program. Professor Nicholas Turrow teaches chemistry at Columbia University in New York.
We have to flip a spin or rotate a spin around somehow in order to get it to deactivate.
A leading researcher in the area of photochemical mechanisms, he was appointed professor when only 26. Already, his research triumphs are becoming the stuff of chemistry textbooks.
So it's what you would call a textbook example of a photoreaction, one that if a student was going to start into photochemical mechanisms, one would well advise a student to read about the history of valerophenone and model your attempt to elucidate the mechanism as close as one could to that analogy.
The valerophenone mechanism is the subject of this program. Our other chemist is now director of the Energy and Process Lab at the Allied Corporation in New Jersey. His name is George Hammond. As well as being something of a photochemistry pioneer, George Hammond is well known for the ability to communicate enthusiasm for his subject. How does he view the successful work on valerophenone that was started in the early 60s?
Now, I'd like to tell you that these kinds of fragmentation reactions controlled by now more exquisite knowledge of microphysical detail have led us to momentous accomplishments in, let's say, the synthesis of highly glamorous natural products of medicinals. They haven't.
That's often the case with pure research. It's rather like mapping out the details of a terrain before anyone's decided whether they really want to go from A to B or not. This is valerophenone, or 1-phenylpentan-1-one. It has an aliphatic backbone with a phenyl substituent, and it was this phenyl group that made the molecule interesting. Previous work had already established the mechanism that occurred in purely aliphatic ketones. George Hammond wanted to see whether the change from all aliphatic to half aromatic would affect the mechanism.
That's really the question that stimulated us to begin the work. The answers we got out actually turned out to be fairly interesting, and again, not entirely what we'd anticipated.
This is a reconstruction of one of the first experiments. The idea is to irradiate valerophenone with ultraviolet light. Now, to decide what wavelength to use, he had to find out where it absorbed.
There are no surprises in the spectrum. You see a low intensity maximum, maximizing about 330 nanometers, and a considerably higher intensity maximum in the shorter ultraviolet. So, at least initially in planning the experiment, we have considerable latitude in choice of the wavelength of light that we're going to take out of our mercury lamp. And we make a choice on the basis of partially convenience and a little bit of caution.
It's convenient to use a mercury lamp with a filter solution to select the fairly strong line at 313 nanometers, rather than the higher energy lines below 300 nanometers.
If you put in higher energy photons, you may get a little more extra photochemistry and begin with unwanted complications.
At the same time, George Hammond's former student, Nick Turrow, was also looking into the irradiation of valerophenone.
What one normally finds most convenient is to have a light source. The problem with photoreactions is to capture as much of the light from the source as you can. And a source which is cylindrical in nature is usually best, so that one has a cylinder, light is coming out in all directions, and the problem of capturing the light can be well handled by simply having a vessel in which the lamp can be immersed. The size of the vessel can vary, and the amount of light absorbed can be adjusted by changing the concentration of the material in the vessel.
To filter out the radiation below 300 nanometers, the lamp housing has a yellow solution of potassium chromate flowing through it. To keep oxygen out, the solution is purged with nitrogen. This also keeps the solution stirred. UV radiation is harmful. Even though this is only a small mercury arc lamp, the operator must protect his eyes. The irradiation can take several hours, and it's important to know if anything's happening. Fortunately, there's a marvelous technique for looking at fairly volatile reaction products.
We set up a gas-liquid chromatography analysis designed to detect those products which we anticipated, at least the majority of them. We ran the reaction, the radiation, took samples, placed them in the GLC apparatus, and saw peaks. And the peaks were where we thought product peaks should be.
The goal now is to be able to identify every peak that we see that wasn't in there to begin with and that we understood the nature of. There are various ways one can now handle a problem from this point. A quick way is simply to collect the peaks as they emerge from the GLC and then take some spectral analysis of these.
This is a preparative GC. It only uses a small fraction of the sample for detection. The rest passes to a cold trap where it's condensed and collected for structure determination. And this is what they found. There were 3 products: acetophenone and propene produced by a cleavage reaction, and also a small amount of this cyclic compound.
And so a lot of what we do when we study reaction mechanisms is try to dissect reaction processes into things we call elementary steps, simpler reactions. Now, I must say that there's kind of a never-ending quest to this, because it seems that you can always take the already simple and make it simpler, break it into smaller and smaller steps, and so I have to caution that this can't go on without limit, or you spend all the time chasing a rabbit and then cooking a stew at the end.
The next question that Hammond and Turrow wanted to answer was this: if valerophenone is photochemically active, one or more low-lying excited states must be involved. What are they?
In order to answer this question, we do a little theorizing first. We look at the absorption spectrum and see these 2 bands, one a strong absorption below 300 nanometers, one a weak absorption above 300 nanometers. The low intensity of this long wavelength band marks it as being what we call an N to pi star transition. These characteristically have very low intensities, and so this is just as it should be. The shorter wavelength, more intense band is expected to be there, and we therefore assign it as a pi to pi star transition. Now, these are excited singlet states, because one of the very good rules of absorption spectroscopy is that changes in spin multiplicity don't occur in transitions which occur with any significant intensities. And so we have located an N to pi star excited singlet state, a pi to pi star excited singlet state. Now we know, and I say know as much as I can say this about anything that we derive from theory, that corresponding to each of these excited states, there must also be an excited triplet state.
The properties of the triplet state can be broken down into several categories. First, a triplet state, since it's an electronically excited state, will emit light. However, in contrast to the singlet state, it takes a lot longer for the triplet state to emit this light. Furthermore, the triplet state has a different energy than the singlet state, so the energy of the light coming out will be different. Both of these are characteristics, lifetime and the energy.
Now, if this molecule were benzene, you see it is a derivative of benzene, we would see a short-lived emission called fluorescence. Valorphenone gives no fluorescence. The only emissions that we see are the long-lived emission that we call phosphorescence. Now, David takes the emission spectrum in a way which mechanically looks a lot like taking an absorption spectrum because he makes up a solution. Of course, in this case, he cools it to low temperature. Cooling to low temperature is desirable because these emitting species decay by other means than emission of light. And at higher temperatures, that kind of a decay is almost totally predominant, and it's very difficult to see good emission. But by cooling it down, putting in a spectrometer, irradiating, and now measuring the wavelength of the light output, we got an emission spectrum which we can trace out. Phosphorescence in organic molecules uniquely arises from triplet states, and so when we see this long-lived emission, we know that we're observing a triplet state. Well, the 0-0 band is assigned over here. I think you see the first bump, and we say that this is at least close to the onset of absorption, and this is what we give as the excitation energy of the excited triplet state without added vibrational excitation. We can do a little more dramatic experiment and allow you to actually see something coming out, see some light, by taking this to another laboratory, irradiating the sample with a laser. The laser gives out pulses of light, and we can vary the rate at which the pulses are repeated. And if we do this, I think we can actually show you a little something related to the lifetime of the excited state. See, when we pulse it at a slow rate, you can see discrete flashes coming from the sample. If we up the pulse rate a little bit, I think you can see visually that the rate of flashing is different. Now, if we go 10 times higher repetition rate, your eye can't tell that this is a pulsed experiment. It looks as though it's continuous.
So Hammond and Turrow presented the evidence for low-lying excited states, but only the N-pi star triplet was actually observed by phosphorescence. Lifetime is the means of distinguishing the triplet states. Now Hammond and Turrow knew that by using a substituted valorphenone, it was the longer-lived pi-pi star triplet state that was the lowest. The observation that a small change to the molecule had resulted in the two triplets changing position had implications for the relative energies of the two triplets in valorphenone itself.
We therefore think that we learn that in valorphenone there are two low-lying triplet states very close together, with the N-to-pi star state being the lowest, and slightly above that, the pi-to-pi star state. And so consequently, we now draw up a Jablonski diagram in which we put these two triplet states well below the excited singlet states and very, very close together.
It is a very important exercise in the establishment of any photochemical mechanism to determine which excited states are responsible for the products. Now, for example, if we believe that the reaction was occurring from a triplet state, we could add a material which could interact with the triplet state and cause it to decay at some rate which was competitive with the reaction. We are now opening a new opportunity for the triplet to react, so it won't give us as much of the product.
So the preparative scale reaction was repeated, but with a large excess of quencher present. The quencher was 1,3-pentadiene, or piperylene as it's commonly called. When the GC trace was examined, there was a dramatic change. The product peaks simply weren't there. Instead, there was a group of peaks which hadn't been seen before, Now, these aren't new reaction products, as they occur in other photochemical systems where piperylene is used. So they can be taken as a fingerprint, evidence that piperylene is doing its job as a triplet quencher.
And since it is able to quench entirely the chemical reaction, we know, we have presumptive information to tell us in this experiment with this system that only this lowest lying triplet state of valerophenone is responsible for the chemical changes.
We can also note in passing that since both the main reaction to give the cleavage products and the minor reaction to give the cyclic product have been quenched, both reactions must arise from this excited triplet state.
The merry-go-round is a device which was developed at Caltech during the early 60s, and it was intended to solve a problem that the photochemist has, and that he would like to inject the same amount of energy into a number of different samples. So one way to get around this problem is simply to pass samples around the lamp many times in such a manner that we will have an integrated situation, and one will not have to worry about different amounts of light being absorbed by the different samples.
This homemade toy played an important part in the next assault on the valerophenone reaction mechanism. The idea was this: to have a different concentration of quencher in each tube and study the effects of this quantitatively. Clever, isn't it? As before, GC analysis was used to determine the amount of product in each tube and obtain a Stern-Volmer plot. From the slope of the straight line, we can calculate the lifetime of the triplet state. It may come as a surprise to learn that this homemade toy revealed the lifetime to be less than 100 millionth of a second. But what happens then to the triplet? Even in chemistry, you often need to speculate before you can accumulate.
As a matter of fact, I was much impressed with the stories of Kekule's conceiving of benzene when he was having some sort of a pipe dream and waking up inspired. And I realized for a long time that I sometimes dreamed about chemistry, and I was very ambitious to capture the genius in these dreams. And once, by dint of great effort, I managed to wake up during one of the dreams and recapture what I'd been dreaming. It was such utter rubbish. I totally gave up that act.
Nevertheless, Hammond wasn't inhibited about speculating on the valerophenone mechanism.
Now, at the time we were doing our work a few years ago, we speculated as to what happened next. And we speculated that the triplet state of the ketone would abstract a hydrogen from a remote position in the aliphatic chain, give a biradical, and this biradical would then fragment to give propylene plus the enol form of acetophenone, the product ketone.
Let's look a little more closely at Hammond's speculation. Abstraction of this hydrogen gives this biradical, which is an attractive intermediate because, as well as cleavage here to give the main products, it also offers a route for the production of the other product, this cyclic compound. But it's still all speculation, and the existence of the biradical is the most tenuous link. Could they prove it actually existed?
The biradical, as long as it lives, is like any other chemical species. Its main peculiar property is it doesn't last very long. It may last of the order of tens of nanoseconds to a microsecond. So we just have to be rapid in terms of the way we analyze the product.
As you might expect, the technique used here is flash photolysis. A UV laser irradiates the sample. The monitoring flash is a continuous light source with a shutter arrangement.
In this case, a flash of light would go through the system. The diradical has an absorption. That absorption can be tracked in time. It can be displayed as a normal absorption spectrum, and models can be used to decide that it truly is the biradical that we have observed. One should remember that around 1965, notion of representing a biradical in a mechanism was considered by some to be a mnemonic device, and that these biradicals didn't have any true existence. So one of the surprises that came along was the ability to actually see these species in flash spectroscopy, measure their absorption spectra.
With the triumph of proving that the biradical really existed, the next step was to show that the cleavage to acetophenone took place through the enol. The experiment Nick Turrow did was to run an NMR spectrum after irradiating valerophenone within the spectrometer.
Enols are generally very unstable in equilibria with ketones. However, they are materials which are produced and have a certain lifetime. So for example, if one did the irradiation of valerophenone at low enough temperature, these enols might persist.
A perspex rod serves as a light guide. The light travels down the guide and irradiates the cooled specimen. Can the enol form be detected? Here it is. Raising the temperature causes the enol peaks to disappear as the enol converts to acetophenone. So this confirms that cleavage of the biradical leads directly to the propene product, but that acetophenone is preceded by its enol form. And that's it, the mechanism of the photoreaction of valerophenone.
It's very easy to get seduced by the power of our own words and think we're talking about an absolute physical reality. We're not. We're talking about a model, which is a construct of the human mind. And if you remember that, then you get in a very comfortable situation of not deciding is the model absolutely right or wrong. It's how good is the model? How well does your thinking with this model enable you to predict and simulate the behavior of systems as you see them? And that's what I feel comfortable with.
There was one day when we started talking about molecules, as if they were these little balls that matter was made out of. And one talked about how a liquid would go to a gas and how a liquid would go to a solid. And thinking about things in these terms, I found tremendously exciting intellectually. And it suddenly became clear to me that the entire world around me might be viewed in this manner. Now, it didn't seem to be much of a concern to me whether this was true or not, but it seemed like a really delightful way to think about the world around you.